This lecture is going to focus on a concept called the solar nebula hypothesis. So the word solar means sun. The solar nebula hypothesis refers to the formation of our own solar system, the system of planets that revolve around our sun. And this happened about 4.635 billion years ago, which I'm going to refer to as time zero. Now we know that from our video on the Big Bang that the universe itself began over 13 billion years ago. And we also know that the Earth is about 4.56 billion years old. So you can see obviously that the creation of the solar system occurred prior to the creation of the Earth. So this story is going to start where the very beginning of our solar system began forming and end when we have Earth today. Well, not today, but Earth 4.56 billion years ago. But I'm going to refer back to the initial formation of the sun as time zero, and there'll be a handout that you can fill in while you listen to this lecture. And I just think it's like a nice way to kind of organize a lot of different ideas that you'll be learning in this particular lecture. So prior to the sun forming, there was a really loud not loud, but large dust and gas cloud. And that dust and gas cloud that will eventually become our sun and our solar system was hit by a shock wave. And it from a nearby supernova. A supernova is the explosion of a star. And so it's important, a really important concept to keep in your mind throughout this lecture is the idea of gravity, the idea that particles are attracted towards each other based on their masses. That's going to be a concept that we talk about throughout this lecture. So when this sort of disorganized cloud of dust and gas was hit with some energy, we know that particles that are at rest will stay at rest until something moves them, and particles that are in motion will stay in motion until they stop because a force counteracts them. Well, so this energy from this wave triggered these particles to go into motion. And as soon as they started in motion, they started responding to gravity. And they started becoming attracted to one another based on their own mass. And this gravitational collapse resulted in the creation of little gas and dust pockets about 50,000 years after time zero. So you have this very slow, 50,000 year long collapse of dust and gas into these pockets. And it's important to remember that K stands for 1,000 here, so 1,000 years, because A is annum or years. So what this created is actually several little pockets that will all eventually become stars. And so astronomers describe this as a star nursery. And our own particular solar system collapsed into a disc-like shape that is now our series of planets and sun. So we have this series, again, 50,000 years after that shock wave hits our solar nebula, we start to have the creation of several stars in our galaxy, and they turn into a disc-like shape. Our sun begins to form about 100,000 years after the initial shock wave hits our solar nebula. And it's not burning near as hot yet, and it's considered a protostar. Protostar means pre-star, and that's because we don't have any nuclear fusion going on there yet, but we're going in that direction. So all the material initially begins collapsing around the center of our solar system. And again, that's that idea of gravity, where materials are attracted to other objects' mass. And so as you begin to accumulate more mass, more objects will be attracted to you, and then once again you have more mass, and so on and so forth. So this process continues for a while, and eventually, just like when you have any sort of spinning, the lower density materials tend to fly out a little bit further than the high density materials. So the low density materials, when they spin, they fling out further from the center. And they disperse to the outer solar system about 1 million years after time zero. So the denser material stays in the center. The lowest density material, which are typically gases, float out from the center. And so the denser material, which is less than 5 million miles or so from the sun, is what's called the rock line in our solar system. So most metals and most minerals are found within the rock line, and that's for two reasons. It's primarily just a mass issue. So metals and minerals are heavier, they're going to stay closer to that center of gravity. Whereas the lower density materials like gases are going to fling out further from the center of this rotating mass. And that's called the snow line. The snow line are regions in the solar system that are cold enough for not only water to freeze, which is H2O, but also methane, which is CH4, and ammonia, which is NH3, to freeze. These are going to be molecules, especially methane and water, that we talk about multiple times in the semester. So that might be something that you want to maybe make a flashcard or a note for yourself on the side of your notes page, that H2O is water, CH4 is methane, ammonia is less important to our discussion this semester, but methane definitely super important. So as particles begin to travel to the snow line, while we have this rotating mass of dust and gases, what begins to happen is they get cold because they're, again, more than 5 million miles from the sun. And when they get cold, they start to freeze. And we start to have the accumulation of microscopic particles that are freezing. And you can see that in this picture here, sort of in the outer portion of our solar system. So accreting is another important word that we'll use multiple times this semester in a variety of contexts. Accreting just means that stuff starts to stick together. So if you've ever had to pick up like Play-Doh after a kid has played with Play-Doh, and you might have a little bit of green Play-Doh, and then you have like a little tiny ball of blue, and you stick it together just because you're going to clean up the Play-Doh and toss it at the end. Anytime you're adding Play-Doh to that ball, you're accreting Play-Doh. You're adding to it. And so these microscopic particles first begin forming, and then they begin sticking together because they're gravitationally attracted toward one another. And this process is going to continue beyond the snow line, where we now have this accretion of methane, frozen water, and frozen ammonia. These particles start to stick together enough that they form celestial bodies that astronomers call planetesimals. About 2 million years after time zero, when things start to cool off just a touch in the outer portions of the solar system. So how big is a planetesimal, which is what this picture is supposed to illustrate? A planetesimal is not particularly large. It's 0.5 to 1 mile in diameter. So this is just the very beginning of planets in our solar system, because we have the accretion of lots of these little particles into planets. So eventually, this will continue to accumulate, and you'll have planetesimal after planetesimal then start to accrete together. We're building bigger and bigger celestial bodies. And eventually, those planetesimals will accumulate into what's called a protoplanet, about 3 million years after time zero. A protoplanet is sort of a baby planet, a pre-planet. The size of a protoplanet is about the size of our moon. And for comparison, our moon is about 1/4 of the size of the Earth. So we have the accumulation of protoplanets about 3 million years after time zero in the outer solar system. And that's where we have the formation of our outer planets in our solar system. Jupiter, Saturn, Neptune, and Uranus collide with a series of protoplanets to grow into these giant gas monsters that they are, where we have, again, frozen ammonia, frozen water, and frozen methane. So as these giant planets begin to accumulate and accrete more and more protoplanets, they then develop a larger gravitational pull because they have more mass. So this leads to a period of rapid growth for planets in the outer solar system. Closer to home is the growth of our sun. So as our sun continues to have material collapse towards the center because of the mass of the sun, you begin to have a process called nuclear fusion that occurs in the sun. Nuclear fusion is when hydrogen and hydrogen atoms hit each other at such a high velocity that they actually merge. And each of these has an atomic number of 1. When you add these together, when they combine, they form an element called helium, which has an atomic number of 2. So there's 2 protons that converge and they fuse together to form helium. And that occurs about 50 million years after time 0. The next thing that starts to happen is that it finally gets cool enough closer to the sun where we can start to have protoplanets form close to the sun. So remember, protoplanets are half a mile to a mile in diameter in our inner solar system. And that includes Mercury, Venus, Earth, Mars, and then the asteroid belt that exists between Mars and Jupiter. So the asteroid belt that exists between Mars and Jupiter is believed by many astronomers to have been a failed planet. So astronomers think that initially a planet did form in this region, not that dissimilar from Earth and Mars in terms of composition. And then between the dueling gravitational poles of the Sun and Jupiter, that once it was under tremendous pressure, being pulled in opposite directions. And so it's likely that when a protoplanet then hit this planet that was already under incredible tension, that the planet actually ripped apart and became what we know today as the asteroid belt, which is kind of a cool story, I'm not going to lie. And so that asteroid belt is actually going to be really important in just a few slides. So we start to have the growth of planets in the inner solar system, including Earth. And Earth was not a great place when it first formed, which we'll talk about in subsequent chapters. But about 75 million years after time 0, Earth formed. At the time, there was another protoplanet that was very close to Earth called Theia. Well, astronomers have called it Theia. And Theia came closer and closer to Earth, attracted by its gravitational pull, and eventually collided with Earth and produced, with its collision of Earth, our moon, which is a combination of the makeup of Theia and some of the composition of the early crust of the Earth, which we'll talk about in our chapter on the Hadean Eon. This is a nice dramatic story that leads us back to this particular diagram where we see why we're even talking about this. So the age of the Earth can be inferred by studying some of those meteorites that are found in the asteroid belt between Mars and Jupiter. So here is a picture of what's called an iron meteorite. An iron meteorite is actually believed to represent the core of the failed planet that existed between Mars and Jupiter. And what we can do is use 2 isotope systems that have really, really long half-lives. We can use the uranium-lead dating system, and we can use what's called the rubidium and strontium isotopic dating system. Again, you can find all of these isotopes, not isotopes, but you can find all these elements on the periodic table on Blackboard. And so by analyzing these iron meteorites and making a couple assumptions, we come up with an age of 4.56 billion years for the Earth. And that's corroborated between the uranium-lead system and the rubidium-strontium system. So why do we think that the core of this failed planet is the same age as the core of our own planet? So that's because we have the assumption that all of the planets in the inner solar system began forming around the same time because they would be approximately the same temperature. And their compositions might vary a little bit between Earth, Mars, and this failed planet, but not appreciably. So it's likely that just as the planets in the outer solar system began to form around the same time, that the planets in the inner solar system would similarly begin to form around the same time. Which brings us to the end of our chapter. So this chapter about deep time started talking about the geologic time scale, which is broken from eons, being your largest chunk of time, to eras, which are broken into periods, which are broken into epochs. We learned that the geologic time scale was initially constructed using relative time dates, but the dates were added afterwards with the advent and understanding of radioactive dating. We learned that there are 3 different types of radioactive dating. and or radioactivity that results in the creation of daughter products. And those are alpha emission, where you have 2 protons and 2 neutrons that are ejected from a nucleus. Beta emission, where you have a beta particle that's ejected from the nucleus in the form of an electron. And then electron capture, where an electron is absorbed into the nucleus, where it combines with a proton to form a new neutron. And then finally, we talked about the solar nebula hypothesis in this lecture, and how by understanding the solar nebula hypothesis, we can understand how geologists and astronomers came up with a calculation for the age of the Earth using iron meteorites. We're going to be talking about stony meteorites in a couple chapters also. Stony meteorites are believed to be the mantle of the failed planet. So these are not small ideas, and I hope that that little handout helped kind of organize all the things that you learned in this lecture, because there's a few steps and they're all kind of significant, and but can be easily confused. All right, hope that helped.